Okay, we've started recording and I'll take you to the practice quiz. Problem 1, what is a critical point? Give its definition and describe it graphically. So don't do number 2 yet. It's related, but I want you to have all the aspects of number 1 at your fingertip when you do number 2. So don't look it up in your notes, just what can you remember?
Javi le ayudó también. Estoy tratando de ver una movie. Javi te va a ayudar.
Okay, anybody still need more time? Critical point? Alright, so the definition of a critical point. Let me just double check my mic is open. And, alright, looks good. Alright, so what is a critical point? It's a point on F where f prime of x equals 0. So it's an x-coordinate where the derivative is 0, but not quite just that. Or f prime of x, and this is an important one that often gets overlooked, does not exist. It's both. And then describe its graphical significance. Alright, now one way to describe it graphically is if you've got a graph doing this, then the critical points where the derivative is 0, where it has a horizontal tangent line, they tend to be maxes and mins. In fact, if they're going to be a local extrema, they have to be a critical point, unless it's an endpoint. But you could have a horizontal tangent line right here, where it got to be horizontal. This is rare, but it can happen. It happens in y equals x cubed. It's a classic example of this. The horizontal tangent line, and then it changes its tendency right at that point. And so it's horizontal tangent line at 0, but so because of that, it's where it's not necessarily a max or min, but typically it is. And so graphically, it's usually a local max or min. We have to put usually because of things like the x cubed curve. Also, it usually divides the graph into regions of increasing, decreasing. Now, we can see that over here. To the left of that blue dotted line, it is increasing. To the right of it, it is decreasing. And then to the right of it, it is increasing. But then it's increasing again, so it didn't divide it up over here, even though there was a critical point. So that's why we say it usually divides into regions of increasing, decreasing. Okay. So there was a lot of graphical significance with critical points. All right. Give me a little feedback on that. Were you remembering most of this stuff? Or only portions of it, and so on? Okay, difficulty putting in words. All right. All right, now, inflection points. Give its definition, describe it graphically. You got a little bit of orientation with the previous one. Try to get as many aspects of this as you can. All right, anybody need more time on this? Okay, so an inflection point. It's a point. Usually we think, it's a point in space. You could say the x and y coordinate, or you could just say it's the x coordinates of the points where the second derivative is 0, or very similar to this one, or f prime prime of x does not exist. This is very often forgotten, especially with inflection points. But for instance, if you get an expression that is for the f prime prime that's 7 over x minus 5, then when x is 5, your denominator is not going to exist. That needs to be treated as an inflection point. All right, now, describe inflection points graphically. If we went back up over here, the inflection points tend to be halfway. They have a tendency to be halfway between critical points, and they separate regions of concave down, in that case, from regions of concave up. And then there's a region of concave. Now here's another inflection point. See, because we're concave up here, and then we're concave down, and then we're concave up. And, all right, where, now this one, it says usually, there's two things. The second thing that I stated graphically divides into regions of increasing, decreasing. Let's put that over here. And I'm going to enter that in as text here. Well, take my text. All right. Divides graph into regions of concave up, down. Okay, so it's where the concavity changes. And then if we went to something similar to this one, where it's usually a local max or min, all right, this one is more subtle, and we haven't gone over this yet, so this will be kind of new information for you. It's where the slope is steepest. So, for instance, look at this curve up here at the top. If you were skiing down this hill, when are you going downhill the steepest? Right at the inflection point. And then, not so steep. And if you were rock climbing and you were climbing this next hill, when is it the steepest? Right at the inflection point. F prime is the derivative of the original function. F primes are talking about the slopes of the original. F double prime are kind of talking about the slopes of the, well, I'm not really, why is it where the slopes are the steepest? F prime is extreme points of F, and F double prime, setting that to 0, gives you extreme points of F prime. So extreme points of F prime would be the steepest slopes, because F prime is all about slopes. All right. How are you with inflection points? Are they almost as good? Are you almost as clear with them as critical points? Or is it more fuzzy? Just give me a little feedback here about inflection points. All right, let's go to number 3. This is a situation.
Professor, I'm so
Yeah.
sorry. So going back to your original graph, there's just the one question. If you look at, I guess, the green one that you have there, where you show that you have a horizontal tangent, but why is that not an inflection point? I know that it has a slope of 0, but it looks like the left of it, it's concave downward, and then to the right of it, it's concave up.
Ah, okay. I think you are correct. That would also be an inflection point as well. And now and then, the inflection point and the critical point can coincide. They can be right on top of each other. So, and that's one of those cases. To the left, it's concave down. To the right, it's concave up. And it's also a critical point because the tangent line is horizontal right there. Thanks for pointing that out. All right, let's go to number 3. Here's a situation where let's assume it's not President Trump. Some kind of sane person is in office, and many of the pressures on a president of a country have to do with the economy. And the press and the president there's kind of a press conference. And we're going to assume that F of t represents the inflation rate. Thus, if you had F of 2020 equals 0.03, that means that in the year 2020, the inflation rate was 3%. Okay, so especially people that donate money to presidential campaigns, they usually have an interest. Businesses have lots of money to give, and they have business interests, and they want to see the economy do better, and they want inflation rate to go down. All right, so the instructions are to write a mathematical statement for the president's response. So the first line is the press response, and I wrote a mathematical statement of that. So the press says, you've been in office now a little while, it's been a couple years. And inflation is increasing each year. So what does that mean in terms of F, the inflation rate? F prime is greater than 0. So if they could state that sentence mathematically, they'd be saying, oh, F prime of t is greater than 0. All right, so then the president responds. Says, you can't expect miracles. I've only been in office a short time. 2 years is nothing compared to the 8 years that my predecessor had that, loused up our whole economy. And since I've taken office, though, inflation is increasing by a smaller and smaller amount every year. It's been going up, but it's going up by smaller and smaller amounts. So give me 4 more years, and I'll make sure that this trend continues, and all of our financial problems will be gone if you just elect me for 4 more years. All right, so when he says, since inflation is increasing by smaller and smaller amounts each year, that's your job, is to translate that into a mathematical statement. So let me give you a minute in your groups. So first of all, try to do this individually, then converse in your groups, and then I'll call on a group in a minute. Anybody need more time? All right, let me go to group 3. What do you have?
We're good at pass on this one.
All right. Let me check on group 4. You have anything? You can also pass if you want.
All right, so we're thinking that it could be exponential decay because it'll be growing smaller and smaller each year. But after that, we got nothing.
Okay, now, you're giving me a visual of this. So is he saying that inflation is doing this? Is that what the president is saying?
Oh, it's increasing by a smaller and smaller amount each year. So would it be like a logarithm function?
Ah, yes, not exponential decay, but I like the way you're figuring this out as we're going along. It's going up, but not going up so steeply. It's like a logarithm function. It's going up by smaller and smaller amounts. So if we had tangent lines, the tangent lines are getting more and more horizontal as we move to the right here. And so he's saying that they increase by smaller and smaller amounts, so it's not this picture, it's this picture. And still increasing, but getting smaller and smaller amounts. Now, how does this relate to f and f prime or f prime prime? By this increasing by smaller and smaller amounts, is he saying, for instance, is he claiming f prime of t is in fact negative? Now, he can't be saying that because f prime of t is positive. Inflation is increasing each year. It's not what he's saying. But then what is he saying? Anybody want to pipe in?
That f double prime of t is less than 0?
That is correct. If what he's really saying is the second derivative. Now, the second derivative has to do with the change not in f, but the change in the slopes. The slopes are getting smaller and smaller. In other words, about f, when f prime prime is negative, we are concave down. So he's saying, oh, it's concave down. The slopes, although my predecessor had really screwed things up and inflation was out of control, going up super, now it's going not nearly as steep. Give me more time and we'll turn this so the trend will keep continuing and actually inflation will go down eventually. All right. What we're seeing in this example is the second derivative is actually more of a longer term trend. The immediate thing is, if you're going to project into next year, you want to know what the first derivative is. If inflation is really climbing a whole lot right now, I'm going to pick that inflation next year is going to be larger than this year. And I want to know what the first derivative is. I want to guess what's next year. But if I'm going to be guessing, 10 or 20 years down the road of what's happening with inflation, I want to know more than just what the first derivative is. I also want to know what the second derivative is. The longer term trend, I'll need the second derivative to say, well, what are happening to those slopes? Are the slopes staying the same, or are they getting smaller, or are they getting larger? Okay. If you're driving a car first derivative, so you have a distance function. Time is the input variable, and how much distance you travel is the output variable. The first derivative will represent your velocity. And you look on your speedometer to see what your velocity is. Your second derivative, though, is whether you're stomping on the accelerator. Suppose you're going on a flat road, then if you're pushing on your accelerator and you're accelerating the car, that's important to know. When you're, in a short amount of time, where am I going to be in 10 seconds? You want to look at what's the current speed, the first derivative. But where am I going to be in 2 hours? You want to look at not just that you're going 10 miles an hour, but that you have your foot on the accelerator and that you're, going to be traveling faster as more time goes on. So you want to know information about the second derivative as well, the change in the first derivative. All right. Give me a little feedback. Was this confusing, or did this add insight onto second derivative and how it relates to a first derivative? Okay. Let's go back. Let me summarize this again, and then maybe in the future I'll put another question that will kind of reinforce this idea. All right. So, first, a summary. The press says that inflation is increasing every year, so they're saying, look at the trend, it's going up. The president said, yes, but there could be worse ways that it could be going up. If it was going up like this, then not only is inflation going up, but it's going up more and more every year. That would be a worse situation. At least my situation is this, where it's concave down. So although it's a bad situation, it's getting better every year, not getting worse every year. We're not increasing inflation, increasing by a higher and higher rate every year. So the concavity makes a really big difference in future projections. And so that's what the president retorts back with, is the long-term trend. And the higher the derivative, the more of the long-term trend. Now there's even graphical interpretations of third derivatives and fourth derivatives and so on. I'll mention, the textbook won't talk about this, but I'll just mention the third derivative. It's sometimes called the jerk. And why is the third derivative called the jerk? Because if you have all of a sudden a big third derivative, like the third derivative was, really, really small, 0.01, 0.01. All of a sudden, third derivative jumps up really big, and now it's 5. Well, that's a sudden change in the acceleration. It's always a change in one derivative less. A sudden change in the acceleration would be like for driving a car and you hit a stop sign. Bam! You're going to jerk. A sudden change in acceleration causes you to jerk. All right, let's go to number 4. Find the critical points of this function and then use the second derivative test to identify the local max and min. So don't graph this, don't use a graphing utility, a graphing calculator, or anything like this. Just find the critical points, and as soon as you find them, as quick as possible, use the second derivative test, find out whether each of those are local max, local min, or possibly neither. Okay, let me give 30 more seconds. You might not have enough time to totally finish, but just get as far as you can. All right, so let's take the first derivative, and the 4 and the 4 cancel out. You get negative x cubed plus 3x squared minus 2x. We're going to be setting this to 0 to find the critical points, but before I do that, I'm going to take the second derivative, because I'm going to need the second derivative for the second derivative test. Alright, so now we set this to 0, and we're going to get 0 equals, and I'm going to factor out a negative x. I like the first term to be positive. I'm going to get x squared minus 3x plus 2. And then that's x minus 2, x minus 1. So these are the critical points. All right, now, if I had a graph, I'd just look at the graph and say, all right, that looks like a local max, a local min, and so on. I don't, but there's a very quick way I can figure out whether these are local max, local min, or neither. We plug them in into the second derivative. F prime prime 0. Because these likely are local maxes or local mins. Once in a while they're neither, but most of the time they're one of those. F prime prime of 0, if we plug in 0 in here, 0 is this term out, 0 is this term out, all you're left with negative 2. So, let's say, is negative. The 2 doesn't matter, the sign of it is what matters, that it's negative. What does that mean? That means it's concave down in that region. It's a critical point, meaning it's got a horizontal tangent line. Horizontal tangent line in a concave down region, it must be a local, change color here, 0 must be a local max. Okay. We'll do a similar thing of 1. Now if we put in 1, I'm going to get negative 3, negative 5, positive 6 is 1. So this is positive, meaning it's a concave up interval. It's concave up in the region where this is, and it's got a horizontal tangent line. So it must be a local min. Let's go to F prime prime 2. If you plug in 2, you get 12, you get negative 12, and you get negative 2 altogether. So it is negative. Concave down, horizontal tangent line. We must be a local max at these 3 values. Now, there's something I want to point out. We didn't have time to go through this last time. But what if you got, if f prime prime, if f prime prime of a critical point is equal to 0. All right. There's the natural conclusion that I would tend to make. If the second derivative is positive, you're a local min. If the second derivative is negative, you're a local max. So if the second derivative is 0, well, it must be the third choice, and you must say, thus, it's neither a local max or local min. But if you use that kind of reasoning, you'll be wrong. Then we've wasted, what is the case, is that we've wasted our time. On the second derivative test. Use the first derivative test. When you get f prime prime of a critical point being 0, it gives you no information about whether it's a local max, a local min, or neither. Now, if it's the case that it was one of these, like this one, so that kind of like y equals x cubed, it's got a horizontal tangent line right at 0, but that's not a local max, nor is it a local min. It will be the case that f prime prime is 0 there, but you'll also once in a while get cases where f prime prime is equal to 0 and you're at a max or a min or something like this. So you can't, just because f prime prime of a critical point is 0, it doesn't necessarily mean that you're neither a max or a min. All right, so give me a little feedback on number 4. If you're able to get part of it, or the whole thing seems confusing, or how it's going. Okay. Correct. Francis's, if f prime prime of a critical point is 0, then the first derivative tests mean look to see if it was increasing and then decreasing to the left and then to the right, and then you know that basically the first derivative test is like draw a little picture of what's going on. And what you're really doing is getting information about where it's increasing and where it's decreasing, so you can draw a rough sketch, and then from your rough sketch you can get it. And second derivative test is where you just don't need a graph at all. All right. Questions on homework. There were some that were input earlier today. What was it? I think that's from a previous day. All right.
You just skipped.
Yeah, what are they?
I think it was number 49.
49?
Yeah, 63 and 50. I think 53.
All right, the earliest one, I'll ask you again later. Let's go to the earliest one, which is 49. We'll start there. Actually, let's get the directions too. 53, I think, was one of them. So we'll grab both of those. And all right, so 49. So locate the critical points. So we're gonna use the first derivative test to allocate local max and min values, find the absolute max and absolute min. All right, so 49, I'm going to focus on C for a moment. To do 49, I'm going to make an x, f of x table. And clearly I need the left endpoint and the right endpoint to plug those in for here. And what points in between might I also need? I find those out by taking f prime of x and setting it to 0. F prime of x is negative 3x squared plus 9. and then we set that to 0, and then I'm going to factor out a -3, and then, alright, so it turns out on this one, x squared minus 3 must be 0, x squared equals 3, x equals plus or minus the square root of 3. Alright, so both of those fit in this interval. And then, so locate the critical points are these two, so that's A. Use the first derivative test to locate the local maximum and minimum values. Alright, so first derivative test would be basically just drawing a rough sketch. So we just, plug these points in, get y coordinates, and then get the coordinates for all of these, and then make the graph. So that's the setup for 49. And let's go to 53. Alright, so this one is on an open interval. And actually it's on everywhere where this is defined. Because ln x, you can't have negative numbers as the input. And the same thing with square root of x. You gotta have positive numbers as your inputs. So we're going to take f prime of x is equal to first times the derivative of the second plus the second times the derivative of the first. Okay, and then we're going to set this to 0, change that to 0, reduce all this. X to the 1/2 over x is 1 over x to the 1/2 plus ln x over 2x to the 1/2. Like this. Alright, now I am going to solve this equation. Before I do anything else, though, it's easy enough to get common denominators. So, what I have is one fraction. Whenever you have one fraction equal to 0, back to the definition of a critical point, where the derivative is equal to 0, where the derivative is 0, if it's a fraction, it'll be just the numerator. Where f prime of x does not exist, that's when the denominator is equal to 0. So a fraction can only equal 0 if its numerator is 0. If its denominator is 0, then the fraction does not exist. But both cases are critical points. So we're going to get a stationary critical point if we're going to get two equations. Stationary critical point if the numerator is 0. But when we solve that, we subtract 2 from both sides. ln x is -2. Remember, we put a base, it's unwritten base of e. So e x equals this to this power, e to the -2 power. So that's going to be kind of a more classic critical point where the derivative is 0. The other one is what we call a singular. something kind of weird is happening. The derivative is going to equal 0. That's when 2x to the 1/2 is equal to 0. But divide by 2, x to the 1/2 is equal to 0. Square both sides, x equals 0. But we don't concern ourselves with this, because the original problem says on the open interval 0 to infinity, we're not even concerned with 0 because that's not in the interval of interest. So outside 0 is outside of the interval 0 to infinity. So we aren't interested. Only interested in the solutions in this interval. All right, so locate the critical points of f. We found it. E to the negative 2. Use the first derivative test to locate the local maximum and minimum values. All right. On 53, since this is kind of different, let's go through it all the way. So I want to use the first derivative test. We only have 2 intervals. So this is e to the negative 2 is the same as 1 over e squared. E is about 2.7, so roughly 3. So this is like about maybe 1/8, 1/9, something like that, small fraction. So the intervals are from negative infinity to 1 over e squared, and then from 1 over e squared to infinity. And then this function was f, so sine of f prime of x. Am I going to get a positive derivative or a negative derivative in each one of these intervals? Okay. F prime of x, let me make things a little smaller here. F prime of x was this expression right here, which is the same as this expression here. And when x is really small, well, when x is, let's just do this one. When x is really big, like 100. ln of 100, that's positive. Square root is positive. So you're going to get positive results right here. And I'm going to suspect that I'm going to get negative. So if I take like 0.0001, well, actually, because yeah, you cannot take anything to the left of 0. So this is actually, instead of using negative infinity, I wasn't interested in that. I'm only interested in 0 to 1 over e squared. And let's try using x equals 0.0001. We know that that's smaller than this. And if I plug that into my calculator for f prime of x, now I'm going to take 1, I know how to store, so I'm just going to put 0.001, store that into x. Oops. 0.0001, store that into x, and then I'm going to go x raised to the negative 0.5 prime, and I do all that, and I get positive again. Anybody else confirming that? Getting positive?
Why are you multiplying it by the exponent of negative 0.5?
I'm using this right here for f prime of x, and ln x times this. Alright, so that's negative. I'm double checking, so hang on with me just a minute. Oh, alright, I did it again, and I'm getting negative. So, let's go. Alright, so now what I can see is that it is, in this interval it is decreasing, in this interval it is increasing, so I'm kind of like drawing a rough little graph. So at this point, 1 over e squared, this must be a local minimum. So 1 over e squared is a local minimum, and then I identify the local max and min values on a given interval. Alright, so the entire function right here, this is increasing, this is increasing. The entire graph is going to look kind of like this, where this right here at 1 over e squared is going to be a local minimum. And I could confirm that by going to like Wolfram alpha. And let's look at my function again. Square root of x ln x. X raised to the 0.5 to the 1/2, that's the square root of x, times ln of x. And that graph is actually negative at first, and then goes up. And as if you took it further and further to the right, it would not be really steep. So my graph here, I should modify that a little bit. The graph comes down and then up, and then it's going to go like this. Alright, so we are at a break point, So let's take a 15-minute break. We'll start again. At 12:46. All right, we're going to get started again. I'm going to go to my camera. I know there was another question on the homework, and if we have time today after the session, I'll go back to answer more homework questions. But I want to make sure I get through today's lesson. So, 4.4, graphing functions. And today, there's nothing new that's going to come. It's kind of combining a couple things that we've already done. So it's a nice chance to kind of regroup and integrate the stuff that we've recently learned. And we're going to start out by looking at this problem, g of x is 200 plus 8x cubed plus x to the fourth. And in the section 4.4, graphing functions, it's assumed that you are not allowed to use a graphing utility. Can't use Wolfram Alpha, graphing calculator, or anything like this. And we're going to have instructions that look something like this. Make a complete graph. To make a complete graph, you're going to need the following elements. 1. You're going to need what I call a master table. 2. You're going to need intervals of increasing, decreasing, and intervals of concavity, where it's concave up and concave down. And then you put these points together on a graph. You're going to need, in the master table, you're going to need these points. You're going to need the y-intercepts and x-intercepts if easy to find. You can always find the y-intercept. Sometimes the x-intercepts are too much trouble, but if they're easy to find, you put those in there. And you're going to need critical and inflection points, all in the master table. All right. So that's what we need to graph this thing. And so come test time, there'll be questions like, here's a function, and make a complete graph for it. You won't get complete credit unless you can do all the different parts of it. And you're not to look at a graphing utility during it. And so let's go ahead and get going on making a complete graph for this function. And let me just check in real quick. All right. So I will take, the first thing is we take the derivative, and we're going to get, the derivative of 200 goes away, I get 24x squared plus 4x cubed. And then I'm going to set this to 0, I'm going to go down from there. I'm going to also take the second derivative. I'm going to set that to 0 and go down from there. This is 48x plus 12x squared. Then I set this first derivative to 0. When I set it to 0, I'm going to factor out what 4x squared is common to both of those. 6 plus x. So x equals 0 and x equals negative 6 are critical points. And then over here, I set the second derivative. Let me turn that in. Set my second derivative to 0, and I factor out 12x. And I'm going to get 4 plus x. So x equals 0, and x equals negative 4 are inflection points. Now notice this function, being a polynomial function, wasn't going to give us any of the harder critical points or inflection points where the derivative doesn't exist. Then we are starting from this information. We can go to our master table. We'll put that way to the right, x, g of x. All right. So to find a y-intercept, you always set the opposite letter, x, equal to 0. When the x is 0, these two terms disappear, and we're left with 200. When you set the y equal to 0, that's how you get the x-intercepts. When you set the y equal to 0, it would be setting this side 0. 0 equals 200 plus 8x cubed plus x to the 4th. Now, there are no easy x-intercepts for this. I'll just write too hard. Okay. If, for instance, if there was an x along with the 200, then an x could have been factored out of all three terms, and then we could say, oh, when x is 0, that forces the y to be 0. And I would get at least one of the easy ones. But if it's not real, it doesn't come real quick like that, we just say, no, we're not going to bother with it. All right. Then, critical and inflection points. We have the critical points. Now, you often get duplication. So 0 was already in here as an intercept. But it's also a critical point. That doesn't mean I have to write it in again. I just might want to make a little note. This is a critical point. And then I'm going to also need to put negative 6 in there. And that's also a critical point. And then x equals 0 is an inflection point, critical point and inflection point for 0. And x equals negative 4 is an inflection point. All right. So then I'm going to find out what these outputs are. And let's see if Wolfram Alpha can give me these outputs real quick. Y equals 200 plus 8x cubed plus x 4 and x equals -6. And it tells me 200 -232. And I'll just change this to -4. Enter again. So Wolfram Alpha has a natural language processor. You're supposed to be able to just type it in like you'd say it, and it will try to figure it out, and very often it can do it. So you don't have to learn any particular lingo to use it. So we get these values in our master table. Alright, so then we're going to make a chart. And we're going to put in 0 and -6, so the critical points, 0 and -4. Alright, so I'm going to need some extra space here. Well, let me first copy this. Alright, to get some extra space, I'm going to get rid of these instructions. I'm just going to write what the critical points are. And inflection points. Okay, and then I'm going to erase this other stuff. And I'll leave the master table. Okay, just doing this because I'll be running out of room otherwise. And, alright, now, last time I showed you how to make a table that shows intervals of increasing and decreasing by using the critical points. What we're going to do is we're going to make that table, and then we're going to insert onto the same table also the intervals of concave up and concave down. So it'll be one large table with all the information about all the intervals of both increasing, decreasing, and concave up, concave down. So we'll start by intervals. Now, if this is along my x-axis, and I have 0 and -6, you see I have these three regions. So the regions are from negative infinity to negative 6, from negative 6 to 0, always open intervals, and from 0 to positive infinity. And then I'm going to be interested, I'm going for intervals of increasing and decreasing. So I'm going to write sine of g prime of x. So, some point in this interval from negative infinity to negative 6, and we're going to need g prime of x. I had erased that. Let me see where is a good place. Let me just write those right here. G prime of x was 24x squared plus 4x cubed. And in its factored form, it was 4x squared 6 plus x. So either of those two, and g prime of x, prime of x, was 48x plus 12x squared, and in its factored form is 12x 4 plus x. All right. So, for any point in the interval from negative infinity to negative 6, like negative 1,000, am I going to get a positive or a negative for g prime? And I can place it into either one of these, into here or here, to figure that out. If I put a negative 1,000, I can see the negative, this term is going to dominate. We'll have a lot more zeros than this term, and it'll be negative, so this is going to be negative. If I'd have placed the negative 1,000 into this one, x squared is always positive, negative 1,000 squared is positive, but that's going to be a negative, so the total will turn out to be negative. And then from negative 6 to 0, I can pick like right in the middle of that, like negative 3. If I picked x equal negative 3, I would get a positive times a positive, which is positive. If I pick something between 0 and infinity, like positive 1,000,000, well, everything's going to be positive. So it's positive. Now, conclusion. About g of x. G of x is, if it's negative, it's decreasing. It's positive slope, it's increasing. Positive slope, it's increasing. So, right here I have my intervals of increasing and decreasing. By the way, I could also make a tiny little sketch. Something like this. And it further is decreasing like this. This is kind of like the first derivative test. Hold it. These should be increasing. I screwed up. I probably want to decrease all the way to the bottom, increase part of the way, and so I have room to keep increasing like this. Alright, so this, at negative 6, we can see negative 6 is a local minimum. And we can see that 0 is neither a local min nor a local max, because it's increasing on both sides. Alright, so this is not new. We did this last time. Alright, what's going to be new is I'm going to take the second derivative points, 0 and negative 4, and append them to right here. Now notice, negative 6 divides these two intervals, 0 divides these two intervals. I need to make new intervals and this time it's going to be for concavity, for concave up and concave down. But when I make my new intervals, the separators are going to be 0, but that's the same as I already had 0 right here. So what I'm going to do is I'm just going to bring this still down to here. My other separator is going to be negative 4. Now, negative 4 is to the right of negative 6, so I'm going to go a little bit to the right of this and bring it down right here. So this is 0, and this is negative 4, is these intervals. Okay, so I'm going to have the leftmost, let me put that, actually let me put these a little bit like this. 0 and negative 4, showing that it divides it up. And this leftmost interval is from negative infinity to negative 4, then between negative 4 and 0, and then from 0 out to positive infinity. These are going to come down. So it's a double layer chart. And I'm going to follow the same pattern, sine of, but now I'm going to put G prime prime x. And that'll tell us about concavity. So if I put any number that's from negative infinity to negative 4 in either here or in here, what am I going to get, a positive or a negative number? Well, let's pick like negative 1,000. I would get a negative times a negative, making positive. Could have also just plugged it in up here and seen that's the dominant term, it's going to be positive. If I plug in a number between negative 4 and 0, let's say negative 2, I would get a negative times a positive, which is negative. So it was quicker to plug it in this one than into this one. Because negative 2, I'd have had to actually square it out and so on. Figure it out up there. And then if I plug in any positive number, like 1,000, well, everything is positive. So it's like this. Now, sine of G prime prime gives a different conclusion. About our original function G of x. Tells us that in this region we are concave up. We are concave down. We are concave up again. Alright. So, what I've got is a master table, this double layer chart that tells me where my intervals, whether it's going up or down, and how it's going up, concave up or concave down, and so on in those intervals. Now I'm going to put them together into a graph, and then I'm done. And I've made a complete graph for this function. So I'm going to have to squeeze it in over here. And I'm mostly interested in to the left of the x-axis, not to the right of the x-axis. So I'm going to go like this. So x, y-axis, and I'm going to go -4 and -6, and I need to go up to about 200 and down to about 230, so let's go by 50s. Alright, and then I'm going to put these dots on my graph. 0, 200, all the points from the master table got to go in there. And that's going to be a critical point, meaning the slope is 0 as it cuts through that point. It's also going to be an inflection point. And then -6, -232, make it around here. That's going to be a critical point. It cuts through horizontally. However I come through this point, I can't come in at a positive or a negative slope. I have to come in horizontally. And then -4, -56. That's going to be an inflection point. Alright. Now, I need to incorporate all the information from this chart into how I connect these points and what I do after these points. And I'm going to pop out a few questions, and anybody can chime in with an answer. So, is it possible that to the very far left of this graph goes like this? Is that possible? Anybody?
Yes.
No.
I hear a yes and a no. Let's go with the no. Who said no? And can you elaborate?
That was me.
Could you elaborate?
I'm saying no because on the interval for sine g prime of x is decreasing.
From -infinity to -6.
Yeah.
Now, I kind of have it decreasing most of the way, but look at that last little portion. It's increasing. That's right. This little tiny bit from here to here is going uphill, so that violates this right here. Okay? That's a good reason why that's not allowed. There's another reason why that's not allowed. Can anybody tell me?
Because I didn't notice that it dipped down, but now seeing that, that it shows that there would be another critical point.
Right here, horizontal tangent line. And we have all the critical points, so it can't be doing that.
Doesn't a concave up mean it's a positive?
Okay, concave up in this from -infinity to -4, it's got to be concave up. Does that look like it's concave up? Does the bowl hold water? I'm glad you brought that up. Yeah, it looks like it's okay. That part of it seems okay. That the bowl would hold water over here, but you can't do this thing. It can't turn around and go there.
So
otherwise it would
that
have
point
a
should
critical.
be the vertex of the concave?
At -4, it's going to wind up, it's going to change concavity. So if it was kind of like looped up like this, then it would kind of loop down for another portion, because then it's going to be concave down on the other side of that. Okay. All right, so what we found out is it could not do this over here. Okay. Let me also throw another thing in there. Suppose from here to here, I go like this. I have to connect these 2 points together somehow. Perhaps they connect like that. Is that possible?
No,
Why not?
because then doesn't it make it concave down instead of concave up?
Correct. It has the wrong concavity, because according to this graph right here, from negative infinity to negative 4, all this region, it should be concave up. So this is actually telling us some specific information over here. And it can be really hard to translate this information into how I do things. And very often how we first start is we just make some guesses like this and say, is this consistent with this? And then we say, oh, no, can't do that. So somehow this has got to be, if I'm connecting these two blue dots, I have to connect them coming underneath the line between them, not on top of the line between them, because that would make it concave down, this would make it concave up. And I have to keep making it concave up. But if I keep making it concave up, my tendency might be to do this. But that is illegal. Can anybody tell me what's the problem here?
Because at -6, that's where we've identified our local min.
That's
And
right.
so,
Local min, and so that should be a
So that should be a slope of 0.
slope of 0. So I was kind of on the right track, but I should have finished it up a little sooner. So concave up. So we have a blue dot here. We got a concave up. Something like that. Now, does that match with all the different portions of here?
No,
Where? Where we have a problem?
-4. That should be a slope of 0, so it can't connect like that. It has to have a
hold
slope
it.
of 0.
-4 was not a critical point. It was an inflection point.
Oh, I see. Okay.
Okay? So it's not a slope of 0, but it's going to change concavity at that point. Okay? And let's look at the decreasing stuff. From negative infinity to -6, we should be decreasing. Is it decreasing? Yes, it is. From -6 to 0, all the way to 0, it's got to be increasing. Ooh, that's kind of strange. But from -4 to 0, it's got to change concavity to go concave down. So, how do I connect these next 2 points? This blue dot here and this blue dot here. I have to connect them. Should I be going above the line that goes between them or below the line that goes between them? Which of those two?
Shouldn't it be above?
It should
Yeah.
be above, so that it's concave down right here. That's right. So you see, it's really easy to connect these points in ways that get the concavity wrong. But we're using everything in our tables to get this all correct. Alright, and then what happens in the very farthest right region? It says we should be
Increasing.
increasing, and it should be concave up. So, am I doing that right?
Nope.
No, I
Nope.
made it decreasing. That's my natural tendency, but hold it, isn't this? This has got to be a horizontal tangent line. So doesn't it have to be a maximum?
But because isn't
Not
one
always.
of the polynomials an x cubed,
That's
which means that it would make
right.
an s?
It's acting like the x cubed, which is right at this point, it's changing its tendency. Although the slope is horizontal, it then goes like this. All right, and so what it does is it changes concavity right there. And so where it's changing concavity, the inflection points are at -4, it changes concavity right here, and then it changes concavity right there. So it's concave up, concave down, concave up again. And we get all the subtleties correct by referring to this chart as we connect our points. All right, give me a little feedback. You think you can do one of these on your own? Is this clear? All right, so let's take a picture here.
Earlier, or I think it was yesterday, that you said that usually between a region of two critical points that your inflection point will fall
Yes.
like along the midpoint. So what would be the exceptions to that? Like what kind?
Here it looks kind of an exception.
Yeah.
Because about halfway between would more be like right up here, but we're having it way over here. The inflection point actually could be anywhere. It's just a kind of a general tendency for most of them to fall somewhere in the halfway region, but it can really vary. I'm glad you pointed that out. That's not a hard and fast rule at all. It's just somewhat of a tendency. All right, let's go to another problem. That's a harder problem to take its derivatives, and we're going to get some unusual things happening, but it's the same idea that we're going to do again in the next problem. And we aren't going to have time to finish it, but we'll be able to set it up. And it takes a little while to get used to the structure of these charts. But the charts also save you time. You don't have to write increasing on this interval and this interval. You just say refer to chart for intervals of increasing and decreasing, etc. All right, so number 2. Y equals x minus 3x to the 1/3. Okay, and the instructions are going to be make a complete graph. If you look on in 4.4 in the problem sets, so many of the problems, like from 15 on to 46, the instructions are make a complete graph of those. And we start by taking y prime, 1 minus the 1/3 and 3 cancel out, x to the negative 2/3. And then we're going to take the y prime prime. The derivative of 1 goes away, I get positive 2/3 x to the negative 5/3. Okay, when I set this to 0, and I add this to both sides, then I cross multiply, then I raise both sides to the 3/2 power, now that bottom number is really a cube root, and that when I raise to the 3/2, that bottom number there is now a square root. When you square root both sides, insert plus or minus. Now, that's one of the advantages of writing it with square roots and so on. If you'd seen this problem like this, x squared cube root equals 1, we'd have looked at the problem and then we'd have said, oh, I got to square root both sides. And when you square root both sides, you tend to remember, oh, I have to insert plus or minus. But when you take the 3/2 power, you might forget that. So that's why we get, these are the critical points. Over here, now I get a fraction equaling 0. When it's just one fraction equal to 0, the only way that can happen is if the numerator is 0. But the numerator is stuck at 2. So this has no solution. But it does have a place where this derivative doesn't exist. If, now anything to the 0 to any power is still 0. So if x is equal to 0, then y prime prime does not exist. So x equals 0 is an inflection point. If it causes the first derivative or the second derivative to not exist, it's got to be considered then either a critical point or an inflection point. That's super important for our tables because you can change concavity across this point. If you don't see that, you'd think, well, same concavity, you'll get the graph wrong. So it has 2 critical points, it has 1 inflection point. So my master table I've got to put my intercepts. When x is 0, you can always plug in x is 0. Figure out what your y is. It's 0 minus 0 is 0. Alright, but 0 is not only an x-intercept, it's also an inflection point. Then we'd also set the y equal to 0. If you set the y equal to 0, alright, so this is for the x-intercepts. Let me write this out. We set the opposite letter to 0. Now, I'm going to factor out what power of x is common to both of these. Take the smaller of the two powers. X to the 1/3 times x to the 2/3 will give you x to the 1. And you get this. So then x to the 1/3 is equal to 0. Or x to the 2/3 minus 3 is equal to 0. On this one, if you raise both sides to an odd power, there's no problem, and we get x equals 0. On this one, we add 3 to both sides. And then we raise both sides to the 3/2 power. It's very similar to what we did over here. But when you raise to the 3/2 power, the 2 in the denominator is really taking the square root of both sides. So you're going to get plus or minus. Okay, now I'm going to punch this out in my calculator. 3 raised to the 1.5 power. And I'm going to get 5, approximately 5.2. Okay, so my other x-intercepts are going to be negative 5.2, positive 5.2. If I plug them in, I'm going to get 0 for the y. Okay. So this was an inflection point and also an x-intercept. These two are also x-intercepts. Well, this is also a y-intercept. Actually, it's a y-intercept as well as an x-intercept, but we had discovered it when we were looking for a y-intercept. Okay. Now we need to also in our master table put all the critical points and the inflection point. Inflection point's already there. So these two are critical points. When I plug them in, let's put in positive 1. I get 1 minus 3, which is negative 2. If I put negative 1, now the cube root of negative 1 is still negative 1. So negative 1, I get negative 1 plus 3, which would be positive 2. All right. Any questions so far? Okay, let's to make our intervals now, the big old table, intervals of decreasing, intervals of increasing. And I'm looking at the homework and 4.4, and I'm thinking that there's too many problems in this homework set, because each of these kind of take a long time. So let me pause here. Let's change the assignment. Four point four assignment. Let's make it like about half these problems. Let's do 7, skip, go to 20, skip, go to 29, skip, go to 36, skip, go to 49. Alright, so that'll be 5 problems, half as many as what's listed on the assignment sheet. If you've got somebody in your group that's not here today, can you communicate to them, let them know that, that the assignment has changed. And right. Now with this information, let's I have to keep that 1 and -1 and 0 are my inflection and critical points, but that's kind of listed over there in the table, master table. So I think I can get rid of most of this. I probably should have kept the derivatives, but they're real quick to find. Y prime is 1 minus x to the -2/3. Y double prime is 2/3 x to the -5/3. Okay. And critical points are 1 and -1. Inflection points is 0. And so now we have our table. So 1 and -1 gives me the interval from -infinity to -1, from -1 to 1, and from 1 to infinity. And then sine of y prime. And if I plug in a negative huge number, then that's going to be huge, but that's going to be a lot smaller. And this number is going to dominate. It's going to be negative. When you cube root a huge number, it gets quite a bit smaller. When I put a number between -1 and 1, let's put in now if I put in 0, I'm just going to get 0. So let's put in 0.5, something like this. Alright. And let me punch that into my calculator. I get positive. And when I plug in a very large positive number, like a million, that's going to be a lot bigger than that. It's going to be positive again. So, conclusion. About y is that it's increasing, decreasing, decreasing. And now, when you get your whole graph at the end, you probably do want to check, and you don't want to run to this too early, but you want to check with something like Wolfram Alpha and see if it's consistent with your picture. And come on, my mouse is stuck. Something's wrong. All right. Well, we're out of time here anyway. So the homework is 4.4. That's the homework assignment.
Can I ask you a
I'll post it
question?
online too. Yes.
After torturing us for the last 2 days, why are you taking it easy on us?
Good question. I don't know. I don't know the answer.
Thank you.
You're welcome. All right. Any other questions? I will see you all tomorrow then. And if I get my mouse to work, I might be able to turn off the recording. Yeah, it's working. Oh, no, it's not.